Welcome back. We're going to round out our first packet for Unit 2 with matrices and their operations. You're going to become familiar with how matrices work, and we're going to do some algebra with them over the next several days, and then follow that up with some calculator work. So you want to pay particular attention in these first couple of days so that you have a good foundation for the rest of these notes. All right, so the way that you measure matrix dimensions is rows by columns. So these are rows and these are columns. There are 2 rows and there are 3 columns. So that's a 2 by 3 matrix. The address is counted this is row 1, column 1, row 1, column 2, row 1, column 3. So each of those addresses is going to be A1, 1, A1, 2, and A1, 3. The value that we're trying to locate is the value of 8. So that's going to be at row 2, column number 3. So we label it as A because that's the name of the matrix. And that's going to be row 2, column 3. And those are subset numbers like that. All right, so I got 1, 2, 3 rows, 1, 2, 3 columns. So the dimensions of matrix M is a 3 by 3 matrix. Always start with rows followed up by columns. The address of the entry at -3 is there. That's at row 2, column 1. So it's M, 2, 1. And then it's asking for the entry at M32. So I'm going to go row 3, column 2, and that is the value of 2. Matrices are pretty straightforward when you're working through them, and some of their operations are pretty straightforward as well. We'll take a look at those next. All right, so the first thing we're going to need to do is we're going to add and subtract matrices. We are going to need to understand that in order for a matrix to be operated on, it's going to need to have the proper structure. Everything about the matrix is based on structure. Without the proper structure, you cannot do any operations to matrices. So please keep that in mind as we're working along. If there is a value in row 1, column 1, in order to add that to another matrix, there has to be a value in that same address in that second matrix. So you'll notice that A and B do not have a dimension match because there is no value in column 3 of matrix A. Therefore, A and B cannot be added together. The term you'll see on that, including in your calculator when we get to it, will be dimension mismatch. That's what the calculator will state. So basically what we're going to do here is we're going to find A plus C. We notice that this is a 2 by 2 matrix, 2 rows, 2 columns, and that's a 2 by 2 matrix, 2 rows, 2 columns, so they have a match. And now we just add the numbers in each address to one another. And that's going to give you your solution matrix here. Next, D minus B. So D is a 2 by 3 matrix, 2 rows, 3 columns. A 2 by 3 matrix, 2 rows, 3 columns. Those dimensions match up, and we simply add the addresses together. Sorry. Subtract the addresses from one another, and that's how you're going to get your solution matrix. C, or on letter C, A plus D. A is a 2 by 2, D is a 2 by 3. That is a dimension mismatch. You do not have the ability to find that solution. The question next is whether matrix addition and subtraction is commutative. Remember, commutative means that I go one way, get a solution, and I can go the opposite way and get the same solution, commutative. Addition it is, because if I add A plus C and C plus A, the same solution matrix will be the result. However, with subtraction, if you add A and C and if you subtract A from C, then subtract C from A, you will not get the same solution matrix. Next, we'll be moving on to multiplication of matrices. Now, multipliers are going to be these numbers on the outside. They're otherwise known as scalars. They're going to change the value of each of the numbers in each of the matrix. So if you think of the matrix as though it's a set of parentheses and you utilize the distributive property, you are on the right track when it comes to multiplying scalars throughout a matrix. So 7 times 1/2 is 7 over 2. Half of 8 is 4. Half of -2 is -1. And half of -4 is -2. So that's how you want to deal with scalars when we're working through the matrix. Now, when we're working through these types of problems, the first thing you want to do is follow order of operations. The multiplication comes first throughout here, and that's going to give me a new matrix of 4, -4, 6, 0, 4, and 2. I use that new matrix, subtract it from C, and that's going to give me my solution matrix. C plus 2D. You'll notice that C is a 3 by 2. That's 3 rows by 2 columns. And D is a 2 by 3. That's 2 rows by 3 columns. That is a dimension mismatch. The reason why we know that is that I do not have a value that I can add or subtract from C in matrix D. There is no value there. The matrix is based on structure. All right, our last one here is going to be finding this solution matrix. Remember, we begin with this right here. And then once you've done that, you get, and I'm going to leave the negative out for a second and just subtract them. So it's going to be 0, -6, 9, 1, 3, -15, and 6. By doing that, I leave it as a subtraction problem, and I simply subtract them through. Okay? All right, following that, we're going to go ahead and look at different operations for finding missing values within the matrix. So basically all we need to do here is understand what actually occurs when we have one matrix being added to another matrix and resulting in a solution matrix. What that means is that I understand that if I add the value in this address to this value in this address, I will be getting this solution in this particular address here. That becomes a very simple algebra problem that I just need to write outside of the matrix and then solve for x. That means that the value that should be in that address of the second matrix is -5. We can likewise do the same thing here, knowing that the value of 2 plus 4 is going to give me the resulting value of y in the solution matrix. 2 plus 4 equals 6. Therefore, y equals 6 is the solution to that particular problem. So it's basically just logic and order of operations that we're following in order to solve these problems. Okay, this explanation here is the way that you know whether or not there's a dimension mismatch if you're trying to multiply matrices. Notice you write the dimensions of both matrices, and if the values on the inside of this are the same, you have a dimension match. The resulting numbers on the outside will be the resulting solution's matrix dimension. If these two numbers don't match up, then you have a dimension mismatch because the way that multiplication works. All right, we're going to go ahead and explore this now so you guys can see what this looks like. So in this first exercise, all we're going to do is we're going to see if these operations here actually can be done. So the first thing I want to do is I want to write the dimensions of the first matrix. That's 2 rows by 2 columns. And then I want to write the dimensions of the second matrix. That's 2 rows by 3 columns. I'm going to circle the inside numbers. If they're the same, I'm going to check that as a dimension match, and then the solution matrix will be the outside numbers, so the solution matrix will be 2 rows by 3 columns. I'm going to do the exact same thing here for this one, and I'm going to say, okay, the value of, or the dimensions of B is 2 by 3. The dimensions of A is 2 by 2. I'm going to circle that. If those numbers don't match, I have a dimension mismatch, so the answer is none, or no solution. Obviously, from this particular exercise, matrix multiplication is not commutative. We have proven that through this small exercise in question number 6. All right, the next thing we're going to address is how to actually multiply matrices. This gets a little bit confusing, so you're going to want to watch carefully and understand this, and you're going to have to apply yourself kind of a little bit more when we get to the practice with this particular exercise. So the first thing I'm going to do is I'm going to write the dimensions of A. Then I'm going to write the dimensions of B. I'm going to circle the inside numbers. They're the same, so I know that my solution matrix is going to be 2 by 2. What I'm going to do next is I'm going to write a big, empty 2 by 2 matrix. Inside that matrix, I'm going to have some values that I add together in address 1. I'm going to have some values that I add together in address 2, 3, and 4. Now it's these values in the proper order that get a little bit confusing. The thing you have to remember is where you are. I'm in row 1, column 1. This is row 2, and this is column 2. This is going to help you when it comes to writing these things in their proper place. I'm in row 1. So what are the values that are in row 1 of matrix A? That is A and B. So in row 1, I'm going to write A and B. Over here, I'm still in row 1. So the values that are in row 1 of the first matrix are A and B. Now I'm going to switch gears and I'm going to look here. I'm in column 1. When I switch from the rows to the columns, I'm going to switch from the first matrix to the second matrix. What are the values that are in column 1 of the second matrix? That is E and G. I multiply those together like this. And I write those here because they will eventually become the multipliers down here as well. All right? Again, I'm in column 2. So I switched from rows to columns, so now I'm in the second matrix. This is column 2 of the second matrix. So when I'm dealing with rows, I'm dealing with the first matrix. When I'm dealing with columns, I'm dealing with the second matrix. So in column 2, I will put in the values F and H. Down here, same thing. All right, now we're going to switch gears back again to rows. When I switch back to rows, I switch back to the first matrix. In row 2, the value is C and D. So here it becomes C, and here it becomes D. C here, D here. So if you can understand how this particular relationship works, it makes it easy for you to input numbers into the matrix. Let's try it again with some number values here. So I'm in row 1, row 2, column 1, column 2. So it looks like that the rows have been put in for me. Let's make sure that's consistent so we understand what we're looking at. In row 1 goes the first row of the first matrix. That makes sense, and it's consistent. In row 2 goes the second row of the first matrix. Again, that makes sense, and it's consistent. Now I'm going to switch over to column 1. When I switch from rows to columns, I switch from the first matrix to the second one. So let's go ahead and write this. Maybe this will help us out. Okay? If we can do that and make that connection, it might make it easier for us in the future. All right, column 1 is going to be the value -1 and 6. Column 1 is going to be the value of -1 and 6. Now I'm switching to column 2, so now I'm switching to column 2 here. So that's going to be 5 and -3, and 5 and -3. Now I multiply all this together to get my resulting answers, and that's how I get my solution matrix in these problems. All right, multiplying b times a if possible. All right, so we'll go ahead and write our dimensions: 2 by 2 and 2 by 2. Now because it says b times a, I just can't circle these like this. I actually have to rewrite it so that I can see it properly. Now in this particular problem it's not going to make a difference, but you just want to get into this habit so that you don't make a mistake in the future multiplying a times b instead of b times a like it states. That means that the resulting matrix is going to be 2 by 2, so let's go ahead and fill this in. Alright, now because b comes first, that's my rows. Don't get confused here, we're just writing what comes first and what comes second. Because it's a 2 by 2 matrix, we're going to do address 1, address 2, address 3, and address 4. Alright, in row 1, alright, let's fill it in, row 2, column 1, column 2. In row 1, we're going to put row 1 of matrix B, -1, 5, -1, 5. In row 2, we're going to put row 2 of matrix B, 6, -3, 6, -3. Times, 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 and times. All right, now we're switching from rows to columns, so we're switching from B back to A. Column 1 is 4 and 8. Column 2 is 7 and 2. I'm going to simplify all of that down, and that's going to give me the solution matrix of 36, 3, 0, and 36. Down here, question number 8. We're asked to multiply A times B if possible. So I'm going to write the dimensions of my matrices. Sorry. Please let me write the dimensions of my matrices properly. That's 3 rows and 2 columns. Okay, so A is a 3 by 2 and B is a 3 by 3. Circle those numbers, they do not match. Dimension mismatch. All right, B times A. That's going to be a 3 by 3 and a 3 by 2. And I can see here that my solution matrix is also going to be a 3 by 2. Give myself plenty of space here to do this work, and then we'll see if you guys can sort this out. So a 3 by 2 means I've got 3 rows and 2 columns. All right, inside of each one, because there's 3 values in each address, we're going to do this 3 times. All right. Row 1, row 2, row 3, column 1, and column 2. Okay. Because we're starting with B, we're going to start with the row of B. In row 1, it's 5, 4, 3, 5, 4, 3. In row 2, it's 0, 1, 2, 0, 1, 2. In row 3, negative 1, 7, 4, negative 1, 7, 4. Now we're going to switch from rows to columns, so we're switching from B to A. Column number 1, 1, 8, 7. And column number 2, 4, negative 3, 8. Okay, we're going to multiply all of those out. Yes, I understand that's going to be a lot of multiplication, a lot of addition, so please be very mindful of what you're looking at when you're doing this, because there are ways to go astray very easily. And I'm going to get a smaller, much more manageable solution matrix of 58, 32, 22, 13, 83, and 7. Multiplication of matrices.